Now, today we want to see how to solve the given non-homogeneous linear differential equation with both constant and variable coefficient by the method of variation of parameters. Now, this method is actually the generalization of the method of reduction of order. In that, we consider y1 is the solution of a associated homogeneous differential equation. Here, we consider y1 and y2 are the two linearly independent solutions of the associated homogeneous differential equation. Then we take the substitution y is equal to a y1 capital A y1 plus capital B y2, where this capital A and B are the functions of x, and then we continue how to obtain the solution by using the method of variation of parameters. Now here, in previous section, we saw that if y1 is the solution of the homogeneous equation y double dash plus px y dash plus qx y is equal to 0, we can use it to determine the general solution of the non-homogeneous equation y double dash plus p of x y dash plus q of x into y is equal to rx. Now, because y1 is the solution of 1, means associated homogeneous differential equation, the function c1 y1 is also a solution for arbitrary constant c1. We replace this c1 by the function v of x and consider the existence of a solution of this non-homogeneous differential equation 2 of the form v of x into y1 or v into y1. This led us to a first order linear equation in the variable v dash that we were able to solve. Now, suppose now that we know the general solution of the associated homogeneous differential equation, we call it as to be the complementary function and denoted by yc. This is equal to c1 y1 plus c2 y2, where y1 and y2 are linearly independent on an interval a less than x less than b, or on the open interval ab. Let us see what happens if we replace both constant in this equation 3 by capital A and capital B, which are the functions of x, or you may write a of x into b of x. Means we take the substitution, put y is equal to a of x y1 plus b of x y2. This is the solution of our non-homogeneous differential equation. Therefore, this equation 4 must satisfy this non-homogeneous differential equation 2. Now, from this, we find y dash first. If we find y dash, then we get y dash is equal to a y1 dash plus b y2 dash plus a dash y1 plus b dash y2. This is our equation 5. Now, for our simplicity, means to avoid the second order partial derivative of unknowns a and b, for that purpose we choose this a dash y1 plus b dash y2. A dash y1 plus b dash y2 is equal to 0. We want to use this equation later on. Remember this equation 6. A dash y1 plus b dash y2 is equal to 0. Therefore, this equation 5 becomes y dash is equal to a y1 dash plus b y2 dash. And then from this we find y double dash is a y1 double dash plus b y2 double dash plus a dash y1 dash plus b dash y2 dash. And then from this equation 4, we call this equation 6a and this 7. From these three equations, we substitute these values in the equation 2. Then we get a y1 double dash plus b y2 double dash plus a dash y1 plus b dash y2 dash plus p of x into a y1 dash plus b y2 dash. We have taken this as to be 0. We take this as to be 0 plus q of x plus q of x into a y1 plus b y2. This is equal to rx. Now simplify this. We get the collect the coefficient of A. This is y1 double dash plus p of x into y1 dash plus q of x into y1. Now collect the coefficient of b plus p y2 double dash plus p of x y2 dash plus q of x y2 dash, and the remaining term a dash y1 dash plus b dash y2 dash, this is equal to rx. Now but y1 and y2 are the solutions of the associated homogeneous differential equation 1. Therefore, y1 and y2 satisfy this differential equation 1. Therefore, we obtain y1 double dash plus p of x into y1 dash plus q of x into y1 is equal to 0, and y2 double dash plus p of x y2 dash plus q of x y2, this is equal to 0. Now substituting this in above equation, we get a dash y1 dash plus b dash y2 dash is equal to rx. We call this as to be equation number 8. And then we solve this equation 6 and 8 for a dash and b dash. I have told at that time we want to use this equation later on. Using this equation 6 and 8, you now give us two equations that we solve for a dash and b dash. Now the solution exists provided that the determinant of y1, y2, y1 dash, y2 dash does not vanish, means this is not equal to 0. But we know that this y1 and y2 are the linearly independent, therefore their Roskian is to be non-zero. Therefore, we know that this determinant is non-zero on the interval a less than x less than b. Means this equation 6 and 8 have the solutions. Now Roskian does not vanish on that interval and we can find a dash b dash, and after finding a dash b dash, we integrating, we obtain a and b, and then we substitute these values of a and b, then to obtain the solution of the given differential equation. I hope you understand this, the method of variation of parameters. This is the just generalization of the method of reduction of order, in which we consider the substitution put y is equal to y1. B, here we consider the substitution y is equal to a y1 plus b y2, where this y1 and y2 are solutions of this associated homogeneous differential equation 1, and capital A and B, these are the functions of x. And then we call this as to be equation number 4. From this first we find y dash, and this we assume that this y is equal to a y1 plus b y2. This is the solution of the given non-homogeneous differential equation 2. Now from this, therefore this y satisfy the differential equation 2. Therefore from this first we find y dash, we obtain y dash is equal to a y1 dash plus b y2 dash plus a dash y1 plus b dash y2. Now, for our simplicity, to avoid the second order partial derivatives of unknowns A and B, second order derivatives, instead of using the word partial, we use the second order derivatives. To avoid the second order derivatives of the unknowns A and B, we choose this A dash y1 plus b dash y2 is equal to 0. We call this as to be equation number 6, and we want to use this equation later on. With this choice of a dash y1 plus b dash y2 is equal to 0, this equation 5 becomes y dash is equal to a y1 dash plus b y2 dash, then find y double dash, and then we substitute these values in equation 2. Then we obtain this a y1 double dash plus b y2 double dash plus a dash y1 dash plus b dash y2 dash plus p of x into a y1 dash plus b y2 dash plus p of x into a y1 plus b y2 is equal to rx. Now collect the coefficient of a, coefficient of b, and the remaining terms. Then we obtain this equation, but we know that y1 and y2 are the solutions of the equation 1. Therefore, y1, y2 satisfy this associated homogeneous differential equation 1. Therefore, we obtain y1 double dash plus p y1 dash plus p of y1 is equal to 0, and y2 double dash plus p into y2 dash plus q into y2 is equal to 0, and therefore this above equation becomes a dash y1 dash plus b dash y2 dash is equal to rx. And then we solve this equation 6 and 8. Our equation 6 is a dash y1 plus b dash y2 is equal to 0. And we solve these two equations for a dash and b dash, and this have the solution if the determinant determinant y1, y2, y1 dash, y2 dash does not vanish. But we know that y1 and y2 are two linearly independent solutions of the associated homogeneous differential equation. Therefore, their Warnowskian does not vanish on the open interval AB. And then solving these two equations 6 and 8, we obtain the values of a dash, b dash, and by integrating we can find a and b, and then we obtain, substituting these values, then we obtain the solution of given non-homogeneous differential equation with variable coefficient by the method of variation of parameters. Now see the example based on this topic. Solve the equation d square plus 1 of y is equal to sec x tan x by the method of variation of parameters. Now this method is applicable for both variable coefficient and constant coefficient. Now here we are able to find the two linearly independent solutions of this associated homogeneous differential equation. We know that how to find it. From this we consider the auxiliary equations m square plus 1 is equal to 0. Its factors are m minus 1, m plus m minus I, m plus I is equal to 0. Therefore, m is equal to I minus I. Roots are complex conjugate of each other and non-repeated. Therefore, the complementary function yc is equal to e to the power 0x into bracket c1 cos x plus c2 sin x. Now here we take the particular solution to find this yp. For this purpose, we put y is equal to a cos x plus b sin x. Here remember that A and B are the functions of x. They may not be constant. Now here, then from this A dash is equal to minus A sin x plus B cos x plus A dash cos x plus B dash cos x. Now for our simplicity, we choose A dash cos x plus B dash sin x is equal to 0. Now therefore, this y dash above equation becomes y dash is equal to minus a sin x plus b cos x. Now from this we find y double dash minus a cos x minus b sin x minus a dash sin x plus b dash cos x. And then from these three equations, is from this equation 2, this is equation 3a, and from this equation 4, we substitute these values in this equation number 1. Then we get y double dash plus y is equal to this. We substitute this value in this equation. Y double dash is from this minus a cos x minus b sin x minus a dash sin x plus b dash cos x plus a cos x plus b sin x is equal to sec x tan x. Now collect the coefficient of A and the coefficient of B from these equations. If we see minus A cos x plus A cos x is 0, minus B sin x plus B sin x is 0, what remains to the left hand side? Minus A dash sin x plus B dash cos x. This is equal to sec x tan x. And we want to use this equation 3. Remember this equation 3. Now we get this minus a dash sin x plus b dash cos x is equal to sec x tan x. And our equation 3 is a dash cos x plus b dash sin x is equal to 0. Now we want to solve these two equations for a dash and b dash. For that purpose, solving these 3 and 5, we get, we multiply this by cos x and this by sin x, and adding, what happens if we multiply by cos x? This becomes b dash cos square x. This for sin x, this cos, this sin becomes 0. This b dash cos square x plus b dash sin square x. Take b dash common. Cos square x plus sin square x is 1, means left hand side you have b dash. Sec x means 1 upon cos x, and we multiply this equation by cos x. This gets cancelled. Only what remains on the right hand side, tan x, means we obtain b dash is equal to tan x, and therefore integrating we obtain b is equal to log of absolute value of sec x. We may read it as to be absolute value of sec x or mod of sec x. Now from 3 and 5, find a dash. We have a dash is equal to sin x sec x minus sin x sec x tan x. This, or a dash is equal to minus tan square x. This, we write this sec x as to be 1 upon cos x. Sin x upon cos x is tan x, means it becomes minus tan square x. Integrating on both the sides, we get a is equal to minus integration of tan square x dx. This is equal to the tan square x. We know that the sec square x plus tan square x is equal to 1. Therefore, we obtain tan square x or minus tan square x is equal to 1 minus sec square x. We substitute this value here, and then integrating this, we get x minus tan x. Do not add the constant of integration. We find the value of a is what? X minus tan x, and b is log of mod of sec x. And therefore, what is the particular solution? Yp is equal to x minus tan x into cos x plus sin x into log of sec x. Therefore, the general solution of this equation 1 is y is equal to yc plus yp, and this is equal to c1 cos x plus c2 sin x plus x cos x plus sin x log of absolute value of sec x. We have seen the theory how to find the solution of the non-homogeneous linear differential equation of second order with variable coefficient by the method of variation of parameters. And also we have seen one example